Welcome back to another video. Let's jump right into the topic of exponential distribution. An exponential random variable models the time or distance between successive events in a Poisson process. A Poisson process is a sequence of random events occurring independently and at a constant average rate, such as lambda over time or space. In this case, the random variable x represents the distance, or time, between two consecutive events. The exponential random variable is derived from the Poisson process, and its probability density function is lambda multiplied by e to the power of negative lambda x. Lambda represents the average number of events per unit time or space. A higher lambda means events are more frequent, resulting in shorter expected intervals. The PDF of an exponential random variable describes how the likelihood of observing a certain time or distance, x, between events decreases exponentially as x increases. The exponential cumulative distribution function is 1 minus e to the power of negative lambda x. The mean of an exponential random variable is the reciprocal of lambda. This is the average interval or distance between events, and the variance is also related to the reciprocal of lambda. The lack of memory property is a unique characteristic of the exponential distribution, which makes it stand out among other distributions. This property means that for an exponential random variable x, the probability of an event occurring in the future is independent of how much time has already passed. If x represents the time until an event occurs, then the property can be described as follows. The probability that the event will occur after an additional amount of time t plus s, given that it has not yet occurred by time t, is the same as the probability that the event occurs after time s. In other words, the past does not influence the future. As a practical example, imagine you are waiting for a bus, and the time between buses is modeled as an exponential random variable. If you've already waited 10 minutes but the bus hasn't arrived yet, the probability that you'll have to wait another 5 minutes is exactly the same as if you had just arrived at the bus stop and started waiting. Let's go over an example together. Assume you receive an average of 18 emails a day, and the number of emails received per day have a Poisson distribution. What is the average and standard deviation of the time between receiving two consecutive emails? If you just received an email, what is the probability that you receive your next email within the next hour? What is the probability that you get no emails for more than 2 hours? Please pause the video here to take a moment and try answering these questions on your own. Let's break this problem into parts and go through it step by step. We know that the number of emails received per day follows a Poisson distribution with an average of 18 emails per day. As a result, we know that the time between emails follows an exponential distribution since this is a property of Poisson processes. To answer the first question about the average and standard deviation of the time between receiving two consecutive emails, we need to find lambda first. Given that the average number of emails received in one day is 18, so the rate parameter, lambda, for the time between emails per day is 18 divided by 24, which is 0.75. The average time between emails is 1 over lambda, which is 1.33 hours. So, the average time between emails is about 80 minutes. For the standard deviation of time between emails, it's the same as the mean for an exponential distribution. Hence, the standard deviation is also about 80 minutes. Let's answer the second question. If you just received an email, what is the probability that you receive your next email within the next hour? For exponential distributions, the probability of receiving the next email within a certain time interval is calculated using the cumulative distribution function, CDF. The CDF for the time between events is 1 minus e to the power of negative lambda x. Plugging in the value of lambda as 0.75, we want to find the probability of x being less than 1, which is the CDF of 1. So, the probability of receiving the next email within the next hour is approximately 0.53. For exponential distributions, the probability of receiving the next email within a certain time interval is calculated using the cumulative distribution function, CDF. The CDF for the time between events is 1 minus e to the power of negative lambda x. Plugging in the value of lambda as 0.75, we want to find the probability of x being less than 1, which is the CDF of 1. So, The probability of receiving the next email within the next hour is approximately 0.53. For exponential distributions, the probability of not receiving any emails for more than a given time is the complement of the CDF. Here we want to find the probability no emails for more than 2 hours when lambda is 0.75. It is the probability of x being greater than 2, which is the same as e to the power of negative 2 times 0.75. So, the probability of receiving no emails for more than 2 hours is approximately 0.22. Here you can see how we can use Python to calculate exponential CDFs, PDFs, and visualize them. We can use the expand function to model a continuous exponential distribution. Here as an example, I have calculated the following probabilities for the email example. If you just received an email, what is the probability that you receive your next email within the next hour? What is the probability that you get no emails for more than 2 hours? Thank you for your attention, and see you in the next video.